All right, we're going to go on to chapter 17. 17 is the same stuff that we did in chapters 14, 15, and 16. It's equilibrium. All right, except we're going to have another K value. It's going to be Kc. All the K values are either Kc or they're Kp. But these are going to be Kcs, but just like when you had your acid, it was called Ka. When you have your base, it's called Kb. When it's water, it's called Kw. In this chapter, it's going to be solubility. So we're going to have a solid going to aqueous ions. And so we're going to multiply those ions. And so this is going to be called a KSP. The SP is for the solubility product. All right. All right, so if we take an insoluble salt, so we have our solubility rules from chapter 4, and we had the one with the halides. All halides are soluble except those that are connected to silver lead mercury. So silver chloride, that is an insoluble salt. All right, and so you have an equilibrium. When you're insoluble, you have an equilibrium. You will have small amounts of ions in solution. So you'll have small amounts of Ag plus and Cl minus. All ions are aqueous, so I don't usually write aqueous every time, but you need to know that all ions are aqueous. And so when you write the Kc, which I told you is going to be, so a Kc for a insoluble salt going to its ions is going to be called a KSP, where the SP stands for solubility for the S, and the P is the product, because when you take your products over your reactants, you get your concentration of Ag plus, concentration of Cl minus. Of course, we do not include any solids or liquids in our Ks, and so the AgCl solid is not put in. And so it is the solubility product because we are multiplying those together. All right, and so just like the other equilibrium chapters, we will do initial change and equilibrium. All right, and so you always, in this KSP, always for KSP, you're starting with a solid dissolving into ions. All right, so it's a solid, so nothing matters in your equilibrium setup for your solid. All right, now if we're doing this in pure water, all right, so we are dissolving the AgCl in water. Your initial concentration of Ag plus is 0. Your initial concentration of Cl minus is 0. It has an equilibrium, and so it has to go to the right. So instead of X for whenever you have an insoluble salt, I call it a plus S. If you want to keep calling it plus X, I don't care. I am going to call it plus S. You can use any letter you want. So at equilibrium, I have S amount of Ag plus and S amount of Cl minus. So when I plug that in here, my KSP is equal to S times S, and so my KSP is S squared. All right, where S is called the, again, this is brackets mean molarity. And so S is your molar solubility. All right, so you're going to give solubility. Sometimes it's going to be given in grams per liter, grams per 100 milliliters. Whatever it's given in, you have to convert that into moles per liter in order to get your molar solubility. So a concentration, the brackets, it's going to be molarity. All right, now note if I had sodium chloride, and we know that all sodiums are soluble. So if we take sodium chloride, and what is understood but not written, like over the arrow here. In order to dissolve silver chloride, of course, we had to add water. Water's not part of the reaction. You know there's water because that's what aqueous means, that you have water. All right, now this is not correct. You would not put an equilibrium because NaCl is soluble. So when it's soluble, it is 100% soluble, which means it's not equilibrium. It is a single arrow going to the right, and you get your Na plus and your Cl minus. So this is 100% soluble. All right, and so whenever you have an insoluble salt, you have a partial solubility. All right, and just like Ka, Kb, your Ksp is always a small number. So Ksp is always a small number because it's insoluble. Very small amounts are going to the right, which means your concentration of products are going to be very small. And so that is going to give you a small Ksp value. All right. All right, so they just do a generic. You're going to have some metal. You're going to have some positive ion and some negative ion, and you get it, your positive and negative ions. Again, your Ksp is called a solubility product. Solubility because whatever comes to the right, that's how much has dissolved, called the solubility. The product because you're going to multiply those numbers together. All right, so AgCl, we already did that one. Now, the second one is a little tricky because you have to remember that the reason why it's not written HgCl is because the mercurous ion is the only diatomic ion that you will need to know. So this breaks up into your Hg2 plus 2. All right, so that's a very unique. Only one that does it is your mercurous ion. Every other ion is monatomic ion. All right, and then you have 2 Cl minus. Of course, if you wrote 2 Hg plus, that would not be correct. If you wrote Cl sub 2 minus 2, that would not be correct. There's only one correct answer for breaking these up into their ions. You have to get comfortable breaking them up into their ions. All right, so when you do initial change equilibrium in water, you started with 0, you're going to end up with S. You started with 0, you're going to end up with 2S. Do not forget to use the coefficient. All right, and when you do your Kc, which is a Ksp because it's an insoluble salt, you have the concentration of Hg2 plus 2 times the concentration of Cl minus raised to the second power. Again, make sure you can write the expression for your K values. Then you plug in the values at equilibrium. So your Ksp, your Hg2 plus 2 is S. Your Cl minus is 2S. And when you square 2S, you get 4S squared. Math errors are the most common here. Your Ksp is 4S to the third. Because when you square 2S, that's 2S times 2S. If you mess that up a lot, instead of writing squared, write it twice. Times 2S again. And 2 times 2 is 4. And S times S times S is S to the third. Do not miss these because of a math error. Your Ksp then is 4S cubed. All right, and so for part C, you have to do periodic trends. You see that As is in the same column as your phosphorus. And so you know that we're looking at here of a Pb plus 2. We have 3 of them. And we have an ASO4 minus 3, and we have 2 of them. Because it is neutral over here, and now we have a plus 6 and we have a minus 6. We are neutral on the other side as well. Charge has to balance. So here, again, in water, we're going to start initially with 0. All right, again, this is a solid. The solid, we don't care. It's not part of our equilibrium. All right, and so it cannot be 0 at equilibrium, so it has to go to the right. So plus 3s plus 2s, do not forget your coefficients. And so at equilibrium, you have your 3s and you have your 2s. So you write your expression for KSP. That is your PB plus 2 raised to the third, your ASO4 minus 3 squared. Now you plug in your equilibrium concentrations. For the lead plus 2, you have 3s. And so you have 3s, and that is raised to the third. For your ASO4 minus 3, you have 2s, and that is squared. All right, so the most common math error in this chapter is 3 to the third. That is not 9. 3 to the third is 3 times 3 times 3, which is 27. So I will write that separate. 27s to the third. All right, and then 2s times 2s is 4s squared. All right, and now so you see that your KSP is equal to 108 s to the fifth. All right, so your KSP, the first one, AgCl, when we did that, the KSP was equal to s squared. All right, and so for Hd2Cl2, the KSP is 4s to the third. For the PB sub 3, ASO4 sub 2, it's 108s to the fifth. So you have to do it every time. There's 4 of the common ones. These are 3 of the common ones. And then there's a couple others that you might see, but 99% of them are the main 4. All right. All right, so again, S is the molar solubility. All right, so in order to find the molar solubility, what you're going to do is you're going to take an insoluble compound, in this case, calcium oxalate. And we're going to put a bunch of calcium oxalate into water. We're going to stir it and stir it and stir it until all of the calcium oxalate that will dissolve has dissolved. And so if we do that in a liter of the solution, all right, so then we pour off the solution, leave the solid behind, and then we let the water evaporate, and then we can weigh it. So we did this, and we see that the mass of the calcium oxalate in 1 liter of solution was 0.0061 grams. And so that is the solubility. And so your solubility for calcium oxalate is 0.0061 grams per liter. All right, except S has to be in molar solubility. So in order to get that into molar solubility, you have to convert grams to moles, just like we did in chapter 2. All right, and so we have to divide by the molar mass in grams per mole. And so you get to the periodic table, and you've got your calcium. I think it's about 40, then you got your 24, and then you got your 32, 64, 8, so about 128-ish. All right, so you'll have a periodic table. You'll get the correct molar mass. All right, 1 calcium, 2 carbons, 4 oxygens, add them up. All right, and so then your grams will cancel, and now you have the correct units, moles per liter. All right, so then you have to write the reaction. CaC2O4 goes to calcium plus 2 and C2O4 minus 2. All right, and so you have initial change equilibrium. This is a solid. We don't care. We don't put solids into our equilibrium. All right, so we started with 0, and so it had to go to the right, plus S. At equilibrium, it is S and S. And so you see that the KSP is equal to S squared. And so you take this number and you square it, and that will give you your KSP. Scroll down, they do this one for us. 28, write it down. Oh, 128, good. All right, and so when you take that, your 0.0061 divided by the 128 as the molar mass, you get your molar solubility of 4.8 times 10 to the minus 5. And so as we did our KSP, we had S, and so you simply take that number and square it to get your KSP for this problem. So when you square your 4.8 times 10 to the minus 5, you get 2.3 times 10 to the minus 9. All right, so that's how you will get from a solubility in grams per liter into moles per liter. You have to use the molar mass. All right, so this one, they said they already converted it for you. So instead of just saying how many grams that they had, they then divided by the molar mass and they gave the moles. All right, so it is found that 1.2 times 10 to the minus 3 moles of lead 2 iodide dissolves in 1 liter of solution. All right, and so it's just asking for the solubility product, and it does say constant, so you need to know the words. What are you looking for? You're looking for KSP. All right, they gave you the solubility, and they gave it to you in the correct units. So they gave you the molar solubility, 1.2 times 10 to the minus 3 moles per liter. All right, so that is then the molar solubility. So now you just have to write the reaction. PbI2 solid goes to Pb plus 2 and 2I minus. So you always have initial change equilibrium. Doesn't matter about the solid. So initially we didn't add any lead or any I minus. So it has to make some. You can't have zeros. So plus S and plus the coefficient of 2S. And at equilibrium, you have S and you have 2S. Then you always should write the expression for KSP. So this is your Pb plus 2 and your I minus squared. Then you plug in your equilibrium concentrations. And so you have your KSP is equal to S for your Pb plus 2, your 2S quantity raised to the second. All right, and so now your KSP is equal to 4S to the third. All right, and they gave you S, and they asked for KSP. So you simply plug it in. So your KSP is equal to 4 times 1.2 times 10 to the minus 3 raised to the third. That's minus 9, and that's 1.6. Yeah, I don't know what that is. We'll go with 1.6, and then we'll multiply that by 4 for 6.2 times 10 to the minus 9. Well, we're going to get the right answer. 6.9 times 10 to the minus 9. So anyway, so you raise that to the third. So you multiply by 4, raise to the third. So, all right, so here, good that they do it a little bit different. You can do it this way. It doesn't make any difference. They have your 2 and then the S, and then it's squared. So that's fine too, because that's the same as 2 squared and 1.2 times 10 to the minus 3 squared. Maybe that way is better to make sure that you don't forget that this is 2 squared and that's 4. All right, so you're going to have a chart. In this case, table 17.1. That's going to give you a bunch of KSP values. And what you'll know is all of the exponents are negative. Every KSP value is a small number. Pick one out of here. Any of these ain't good. None of those is what I'm looking for. Here. Huh. All right, I'll give you the same lousy example I gave the first class. Well, let's see. Can I find a better one? I can't. Okay. That one's just as bad. All right, fine. All right, so I'll give you the same lousy example I gave the other class. All right, so because I just took the first one and then I realized quickly that that was a bad choice, and I will tell you why. All right, so I want to know the solubility of aluminum hydroxide. All right, and so I write the reaction AlOH sub 3 solid in equilibrium with Al plus 3 and 3 OH minus. All right, unfortunately, I wanted this to be 0 and 0, and that's the way I did it with the other class. This class, I'm going to do it different. I'm going to say, well, yeah, I know this is 0, but I do know that we are aqueous, which means we have H2O, which means my concentration of OH minus is 1 times 10 to the minus 7. Usually that amount of OH minus doesn't matter. If you see this exponent of minus 33, that is a hugely negative number or negative exponent. So it's an extremely small number. All right, and so the 1 times 10 to the minus 7 actually has an effect on this problem. All right, and so anytime you have an OH minus and you're in water, you have an initial concentration. It is 1 times 10 to the minus 7. Usually that's so small it doesn't make any difference, and most people will put it at 0. But when your exponent is that small, it does make a difference. All right, and so you have a 0. It has to go to the right, so this is going to be plus S, and this is going to be 1 times 10 to the minus 7 plus 3S. All right, and so then you have S, and then you have 1 times 10 to the minus 7 plus 3S. All right. And so anytime you have a starting concentration, you will ignore the plus 3S. So this one is very strange, and I think I will not complete that one. All right, so I'm not going to give you an example that has an OH minus because then you got to do the quadratic equation. Well, fine, let's do it. All right, so you have 4.6 times 10 to the minus 33, and that is equal to your Al plus 3, which is S, times the concentration of OH minus, 1 times 10 to the minus 7, this is plus 3S raised to the third. All right, and then that's your final answer because we're not going to solve that. That's not a quadratic equation. That is a S to the third problem. All right, so let's do the one I was going to do on the next page. All right, so the example that I was more looking for, but they don't have one up here for me. So I'm going to go with lead chloride. So PbCl2 goes to Pb plus 2 plus 2Cl minus. All right, so now the initials are 0 and 0 in pure water. There's H plus and OH minus in very, very small amounts, but there's no lead, there's no chlorine in pure water. And so it has to go to the right. So you got your plus S, you got your plus 2S. So you have S and you have your 2S. And so you have your KSP expression, Pb plus 2, and Cl minus squared. And then you plug in your numbers. So you have your KSP, well, your letters still, that's S times 2S squared. And so your KSP is 4S to the third. So now we know that our KSP is equal to 4S to the third. So in every single one of these, you can solve for the solubility. In this case, you take your 1.6 times 10 to the negative 5, divide that by 4. And then you take the cubed root of that. And you get 1.6 times 10 to the minus 2. That's very odd that it came out to be 1.6, but it did come out to be 1.6 times 10 to the minus 2. All right, so if we go back and look what we did with our calcium phosphate, we actually didn't do calcium phosphate, but we did a very similar one. This is 108 s to the fifth is equal to this. So you'd have to divide by 108, take the fifth root. This is calcium sulfate, so this is s squared. This is cobalt and sulfide, so this is s squared. This is copper and hydroxide. Again, you've got the hydroxide problem, but I should have picked this one. But I was looking for a OH sub 3, or anything sub 3 at the end. I couldn't find another one with a 3 at the end. But anyway, this one is going to have no effect. The 1 times 10 to the minus 3 is not going to affect this one because it's only minus 19, not minus 33. But anyway, so this one is 4s to the third. So if you do this enough, you know what the S value is in pure water. Again, minus 16, it doesn't matter. So you got 4s to the third here. You got s squared here. This one, that's the same as the aluminum one that we did. And that is 27s to the fourth. But that one has the problem with the initial concentration of OH minus. But anyway, you can do all of these and you can get the solubilities. So if the question is which one is the most soluble, you cannot just look at the number. If you're looking at just your KSP, that is not going to do the trick for you. You have to solve for the solubility of that. So you then have to get all the different solubilities and see which one is the most soluble. All right, so you cannot just look at the KSP and say the smallest KSP is the least soluble. No, you have to calculate the solubilities, and the one that has the lowest solubility is the least soluble. All right, so yep, so they do the CaF2. All right, so again, when you do this, CaF2, Ca plus 2 and 2F minus. All right, so then your KSP is your calcium plus 2 and your F minus squared. All right, and so you have your initials 0 and 0, and so you have to go to the right, S and 2S. And so you plug that in, S and 2S. You have to square your 2S. And so your KSP is equal to 4s to the third, and the KSP is given as 3.4 times 10 to the minus 11. So then you divide both sides by 4, and then you take the third root. So that's going to give you minus 12. Third root of minus 12 is minus 4. And that's going to be, I don't know what that's going to be, something times 10 to the minus 4. And that is something times 10 to the minus 4, 2 times 10 to the minus 4. All right, but if you read the problem carefully, this is your molar solubility. All right, so that is your molar solubility, which means the units here are moles per liter. The question wasn't what's the molar solubility. The question was, what is the solubility in grams per liter? So make sure you're answering the question. All right, so not in moles per liter, but in grams per liter. So now you look at the periodic table and you have your calcium, which is 40, your fluorine, which is 19. You add them up, you get 78.1. All right, so then you have to then multiply your grams per mole times your moles per liter, and you see that the moles cancel, and now you have grams per liter. They don't have their grams, you have grams per liter. All right, so here is a question that is saying which of these is the most soluble, and they're not doing what I said you had to do. What I said you had to do is calculate the your S. However, here is your KSP, so this is the list of your KSPs, but this has one lead and one chromium, and so that's equal to S squared. This has one lead, one sulfate. That also is S squared. This is one PB, one S. This is also S squared. So if they all have the same calculation for finding the solubility, if it's all S squared, or if it's all 4S to the third, or if it's all 108S to the fifth, then you can just look at the KSP. So it is very dangerous to just look at the KHPs. It works in the case where it's the same here. It will not work in the case where they are not the same. And so the best thing to do is take the square root of these and get the solubility. So you're consistently always doing that correctly. And so 1.8, that's 1 point something times 10 to the minus 7. And the square root of this is 1 point something times 10 to the minus 4. And this is, which way am I going to go? 5, I think, times 10 to the minus 14. If you take the square root of that, I think it's exactly 5 times 10 to the minus 14. 2.5 times 10 to the negative 27. Square root of that, 5 times 10 to the minus 14. Yes, that's exactly it. So anyway, I don't know what the square root of 1.8 is, but anyway, it's 1 point something. Anyway, it doesn't matter. What you're looking at is the solubilities, and unless you have one that has the exact same exponent, then you have to worry about what these numbers are. All right, but this usually, in this case, definitely tells you that minus 4 times 10 to the minus 4 is the largest number there, so this is the most soluble. And minus 14 is the smallest number for your solubility. That is the least soluble. All right. And of course, if you just looked at the KSPs in this case, that would have worked for you because you did the same thing for all of them to find the solubility. All right. But, many times you're going to have, say, PB, you could have a PBI2. All right. And so that is the KSP given there is 4S to the third. So you have to divide by 4 and take the cubed root. All right, so you have to get the right answer every single time for which one is the most soluble, you've got to solve for the solubility for all of them. All right, so now we're going to do the common ion effect. So that means that we're going to not have both zeros. So far, we had both of them are zeros. So now one of them is going to have an initial concentration. So remember Le Chatelier's principle, if you add a product, the equilibrium shifts to the left. And so that means that less is going to come to the right. The amount that comes to the right is called the solubility. So when you add a product, you are going to have less of your solid dissolving. And so it's going to decrease your solubility. So we can do an example. All right, so we already did our calcium oxalate. We calculated our KSP. Well, first we were given it in grams per liter. We calculated the molar solubility, 4.8 times 10 to the minus 5. And then we squared it to get our KSP. All right, so now we're going to do the same reaction, our calcium oxalate. But initial change, equilibrium, solid is not involved in our equilibrium. All right. So we are not going to add any of our oxalate, but we are going to add some calcium. All right. I'm going to write this reaction, and you should write this reaction every time to make sure you're putting in the right number. All right, so all halides are soluble except for silver, mercury, lead. So calcium chloride is soluble. When it's soluble, you don't write equilibrium. It is 100% going to the right. And so your calcium chloride goes 100% to the right to calcium plus 2 and 2Cl minus. All right, and so now we do initial, and then we're going to do a change, and then we're going to do final, not in equilibrium, one arrow going to the right. And so we start with 0.15 molar. So we're going to have 0 and 0. It is going to go to the right until the calcium chloride is 0. And so we subtract 0.15 molar. So we have to add 0.15 molar. We have to add, and this is where the problem comes in, 2 times 0.15 molar, 0.30 molar. All right, so if you wanted, it was minus x plus 2x. All right, and so we know that this is 100% going to the right, so we know that it went down by 0.15 to give us 0. So that tells us what our x value is, 0.15 molar. And so our calcium is x, that is 0.15 molar, but our chlorine is 2x, which is 0.30 molar. It doesn't matter for this problem because we just want the calcium, so it is 0.15. But I could ask this exact same question using lead chloride. All right, and I could say, what is the solubility of lead chloride in 0.15 molar calcium chloride? Then your initial concentration is not 0.15 molar of the chloride, it is 0.30 molar of the chloride. So you have to know what your concentrations are. The ones that are soluble, 100% to the right. In this case, our common ion is the calcium, not the chloride. And so, again, you still have 0 on the right, so it has to go to the right. So plus S and plus S. And then so your KSP is 0.15 plus S and S. So then we just plug that into our KSP. So KSP is 2.3 times 10 to the minus 9. That is equal to our calcium concentration, 0.15 plus S. But we see that our KSP is very, very small. And so we can neglect any plus or minus X. All right, and so we get our 0.15, and then we have our S. And so in order to find S, we have to divide both sides by 0.15. And that is going to be not sure. Whatever. It's going to be 1.5 times 10 to the minus 8. All right, so that is your solubility now. All right, so when this was a 0, the calcium plus 2 was 0, and this was 0, our solubility was 4.8 times 10 to the minus 5. But when we added a product, 0.15 molar of our calcium plus 2, we add a product, equilibrium shifts to the left, all right? But it is still coming to the right because you can't have a 0, but much less is going to come to the right. And so we see that our solubility decreased by a factor of 10 to the third. So this is 1,000 times less soluble now. All right, so anytime Le Chatelier's principle, you add a product, equilibrium shifts to the left, which means you're going to have less of your solid dissolving. So the solubility will be lowered. Then you can actually divide it and get the actual number. So you had your initial solubility as 4.8 times 10 to the minus 5. Now it's 1.5 times 10 to the minus 8. So it's 10 to the third, so 1,000 is fine, but they actually get 3,000 times greater, right? But anyway, it's a lot larger. The solubility is much, much larger when you don't have an initial concentration of your product. So in water, it is much more soluble than having an ion starting on the product side. All right. So we did zeros for both reactants or both products. We did a 0 for one of the products. Now we're going to do both products have an initial concentration. So when both products have an initial concentration, we are going to find our QSP. All right, they call it QC, they call it KC, but we are doing the KSP. All right, and so the setup, the expression for QSP and KSP is exactly the same setup. However, when you do initial change in equilibrium, when you're using these numbers, then you're calculating a KSP. When you are using the numbers that they give you in the problem, you are calculating a QSP. So that is the only difference. KSP is at equilibrium. QSP is not at equilibrium. So KSP at equilibrium. QSP not at equilibrium. All right, and so in our case, it's usually the initial state. So we put in our initials. All right, and so remember, we're going to compare our Q to our K. So if we see that our KSP is smaller than our QSP, so if here, all right, so that means that the Q is too large. That means the two numbers on the right are too big. In order for those numbers to get smaller, they have to go to the left. All right, and again, if you write the K first and the Q second, the inequality will point you in the right direction. All right, so then the reaction goes to the left. Now, when it goes left on your KSP, you always start with a solid going to ions. When it's going to the left, that means it is forming a solid. And so this is formation of a precipitate. All right, now, of course, the other choice is if your KSP is greater than your QSP. Now your QSP is too small. The numbers are too small. We need bigger numbers. It has to go to the right in order to get bigger numbers. And so reaction, again, if you write the KSP first, it will point you in the right direction. It goes right. And that means that you're going to have no precipitate. So only when you're going to the solid on the left will you have a precipitate. When you're going to the right, you are not forming a precipitate. All right, so we can do calcium oxalate again. All right, so we have our same reaction. All right, so we have our initial change, equilibrium. All right, so again, solid, we don't care about our solid. All right, so we have a concentration of calcium. It is 0.0025 molar. All right, and then we have also a concentration of the oxalate ion, 1 times 10 to the minus 7. All right, so now we have a concentration of both of them. And so we don't know, is it going to go to the right? Is it going to go left? We have to calculate Q and compare it to K. And so your KSP, which is the exact same setup as your QSP, so here's your expression. It is the calcium plus 2. It is the C2O4 minus 2. When you are putting in initial concentrations, then you are solving for the QSP. And so the QSP is when you put in your 0.0025 molar and you put in your 1 times 10 to the minus 7 molar. And so your QSP is 2.5 times 10 to the minus 10. So now we got to compare that to our KSP, which is 2.3 times 10 to the minus 9. And so we see that our Q is too small. Our numbers are too small. Our numbers have to get bigger. So the reaction would go to the right in order to make those numbers equal a 2.3 times 10 to the minus 9, the KSP. So again, you're going to put your KSP and then your QSP and you're going to compare it. So you got 2.3 times 10 to the minus 9 and that is greater than 2.5 times 10 to the minus 10. So the reaction goes right. All right, and that means no precipitate. So when it goes to the right, you're not forming precipitate. That is aqueous. When you're going to the left, then you are forming this solid called a precipitate. So there is no precipitate when you have those two initial concentrations. All right, so just like when we did a bunch of our buffers, every time we did a titration, we had a concentration, we had a volume, we added more volume. All right, so we had to come up with a new molarity. All right, that happens all the time in problems doing precipitation. And so you're going to always have to get the concentration after mixing. So you will have to do MV is equal to MV. Anytime you add some amount of some solution to another amount of a solution, all right, your concentrations of both of those are going to change because you are changing the volume. All right, so here is a question where you're going to be asked if a precipitation is expected. So anytime the question is a precipitation expected, you know that you're going to have your KSP and you're going to compare it to a QSP. And if it's going to the left, then yes, precipitation. If it's going to the right, then no, precipitation. All right, so, but see here, we are adding 50 mils of 0.001 molar barium chloride, and we're going to add that to 50 mils of 0.00010 molar of sodium sulfate. All right, so we've added a volume to a volume. Anytime you are adding a volume to a volume, you got to find a new molarity. And so you got to do MV is equal to MV for your barium. You've got to do MV is equal to MV for your sulfate, because they give you the KSP for barium sulfate. And so we have BaSO4 solid in equilibrium with barium plus 2 and sulfate. So we're going to have our initial, all right, and we're going to have initial of both of them. And so we wouldn't know if the reaction is going to go left or right. We have to calculate our Q, compare it to our K, and see if the reaction is going to go to the right or left. All right, so we have our molarity is 0.0010 for our barium. When the volume is 50 mils, what is the molarity now that it's 100? So that's just dividing it in half. So our initial concentration is 0.00050 molar for the barium plus 2. That's what you get when you solve for that. All right, and then for your sulfate, you got a molarity of 0.00010 at 50 mils. What's the molarity at 100? So divide both sides by 100, and you get 0.000050. All right, and so then we have to have our expression, and in this case, it is 1 barium plus 2, times the concentration of 1 sulfate, SO4, minus 2. So we simply multiply those two numbers to get our QSP, and that is 2.5 times 10 to the negative 1, 2, 3, 4, 5, 6, 7, 8, 8. So 2.5 times 10 to the minus 8 is our QSP. So now, again, we compare our KSP, which is given 10 to the minus 10. All right, so we have our KSP 1.1 times 10 to the minus 10. We have our QSP, which is 2.5 times 10 to the minus 8. And we see that our QSP is much larger. And so your KSP is less than your QSP. And so the reaction goes to the right. Anytime your reaction goes to the right, you have a solid on the right. And so that forms a precipitate. So all of these, when the reaction is going to the right, that would be called the left side. Left, it is a precipitate. Yeah, I'm pointing to the left and I wrote right. Okay, great. All right, so when you point to the left, it is left. And you get a precipitate. So you have a precipitate of barium sulfate formed. Again, if you write your K first, your Q second, the inequality arrow will point you in the right direction, and that is to the left where you get a precipitate. All right, a fractional precipitation. Here is when you're going to have two metals and you want to precipitate one out but leave the other one behind. All right, so you're going to have whatever, doesn't matter what the metals are. Say you have an iron +2 and a copper +2. All right, so you have a solution. It's all in one beaker, and it's iron +2 and it's copper +2, and it's to separate these two ions. If you're trying to separate the two ions, you will have to do a fractional precipitation, which means you're going to precipitate one of them, and so one of them is going to be precipitated. Let's see, I'm not sure. Anyway, you'd have to look at your KSP values. You're going to precipitate one of them. Let's say our iron is precipitated, FeOH sub 2. Turns into a solid before the CuOH sub 2. I would have to look that up and see if that's true by looking at the KSPs. All right. And so what you would have is you would have a solid Fe2OH, Fe ferrous hydroxide would be the solid. The copper +2 would, of course, be aqueous. You would have to look at, so one of them is going to be a solid, the other one is going to be aqueous, and then you're going to filter it. All right, so you would have to find the solubilities of these, and whichever one is the most soluble is going to stay in solution. The other one is going to precipitate. So you would have to add the correct amount, get the correct pH in order for one to precipitate, the other one to not precipitate, and then you're going to filter it. So, of course, your solid is left behind on your filter paper, and the aqueous goes right through the filter paper, and now you have separated your copper and your iron. All right, and so that is called a fractional precipitation. All right, pH has a huge effect on solubility. All right, but not for all of our insoluble salts. What you're going to have is you're going to have a metal with an anion, so generic metal and an anion, X, and you're going to get a metal plus and an X minus. All right, so just generic here. Well, let's do more specific. Let's do AgF and AgCl. All right, so these are both insoluble salts. So we get Ag plus and we get F minus. Here we get Ag plus and Cl minus. So this would be a great question on if I add HCl, if I add acid. So I decrease the pH, so I'm going to add acid. So H plus. And which one of these is going to have an increase or decrease in the solubility? All right, so what's happening here when you take this and you add H plus, the H plus that we added is going to react with your negative ion. And it is going to form an acid. And if you look at this reaction, your H plus plus your F minus is in equilibrium with your HF, you see that that is the reverse of your Ka reaction. So this is 1 over Ka. All Ka all Ka values are very small. So when you take 1 divided by a small number, you get a large number. And so the effect of adding acid to a silver fluoride compound is that it's going to take your F minus and it's going to take it out of the solution. So as soon as your AgF forms any F minus, it immediately reacts with the H plus to form HF. And so the AgF then forms more of the F minus, and it keeps reacting. And so the effect is a large increase in solubility. So this would have a large increase in solubility because we are removing a product. So we made the product, and then the product is being removed by reacting it with the H plus to form your weak acid HF. If we do the same reaction down here, and we have our H plus Cl minus, and that forms, of course, HCl, you have to recognize that HCl is a strong acid, and this goes 100% to the left. 0 is going to the right. So this Cl minus is not reacting with the H plus. It is just staying as H plus and Cl minus because this HCl always has a concentration of 0. All of it is in the H plus and Cl minus. All right, and so when you have a strong acid, there is no effect on the solubility. All right, so you're going to have no change in your solubility if you added acid to the AgCl. You would have a huge increase in solubility if you added acid to the AgF. Again, if you are forming a weak acid, you're going to have a large increase in solubility. If you are forming a strong acid is formed, you will have no effect on the solubility. It will not change the solubility at all. And so when the question says which one of these has a larger effect in solubility when you add acid, you have to see if you're forming a weak acid, that one's going to have the greatest effect. You can put the on it. If they're both weak acids, then of course the weaker acid is going to have the larger increase in solubility. So if they are both weak acids, so if both are weak acids, then the weaker acid has the biggest increase in solubility. So of course a weak acid is weaker than a strong acid. So if you have two weak acids, you will then have to look at the Ka. Of course, the smaller the Ka, the weaker the acid. So look at the Kas, the smaller the Ka, the weaker the acid. All right, and then we look down here and we see that the smaller the Ka, you're dividing by then even a smaller number, you're getting a larger K value for your weak acid reaction. So the smaller your Ka, 1 over a smaller number, you're going to have an increase in that reaction going forward. All right, and so if you have a question here and you have your calcium carbonate versus your calcium sulfate, you see that your sulfate is the, this one's a little more complicated because this one is a diprotic acid. And so when you have your CaCO3 going to Ca plus 2 and CO3 minus 2, you actually have two reactions going on. When you add acid, you're going to have H plus. It's going to react with the CO3 minus 2 to form HCO3 minus, and then you'll also have the H plus reacting with the HCO3 minus to form your H2CO3. All right, and so this is 1 over your Ka1. This is 1 over your Ka2. So this is going to have a diprotic acid. You have a -2. So you actually have 2 Ka values. All right, and so you can look up those Ka values, but when you see that the other one, CaSO4, goes to Ca plus 2 and SO4 minus 2, here you have your H plus and your SO4 minus 2 going to HSO4 minus, that's 1 over Ka. And note, I'm not putting Ka2 because when you have H plus and HSO4 minus, that does not do anything. H2SO4 is a strong acid. It is 100% ionized. Unfortunately, only the first H plus comes off 100%. And so then the second H, it's a very strong, actually HSO4 minus is a very strong acid as well. So anyway, you only have 1 over the Ka for the sulfate. But if you recognize that like sulfuric acid is the acid that's going to be formed with the sulfate, that's a strong acid. This is going to have a much smaller effect on your solubility. It will slightly increase. So this one will slightly increase in solubility. All right, this is going to have a very large increase in solubility. All right, so you have to look at your acids. These are much, much, much weaker acids than these two acids. And so the weaker acid will always have a larger increase in solubility. Again, what's it doing? The carbonate, which came from the calcium carbonate, is being removed. As soon as it is formed, it reacts with an H plus. And so the calcium carbonate is not at equilibrium anymore. It doesn't have the right amount of CO3 minus 2. So it forms more of it, and it keeps taking it out. It keeps forming more of it. It keeps taking it out until it reaches an equilibrium. Once it has reached its equilibrium with this acid being added, a bunch more calcium carbonate has gone to the right, which means you have increased its solubility greatly. All right, so if you add acid to a mixture that contains magnesium oxalate and calcium oxalate, which of the two compounds is more likely to dissolve? All right, so this is when you have MgC2O4 and you have CaC2O4. All right, and so we have our Mg plus 2 and we have our C2O4 minus 2. Note here, we in both of these have the exact same anion, C2O4 minus 2. And so when you add the acid to the C2O4 minus 2, you're going to get HC2O4 minus. Exact same reactions down here. H plus, C2O4 minus 2, and HC2O4 minus. So both of these are going to greatly increase in solubility, but the increase in solubility is the same for both of them. So both will increase in solubility. All right, and it'll be the same increase in solubility because they're making the same weak acid. We're pulling out the same amount of our C2O4 minus 2, making it more and more soluble. All right, so that one would not be more soluble than another because of the acid being added. You would have to find the KSP. So to find which one is the most soluble is all based on what is the KSP. And for both of these, it's S squared. So it is the magnesium plus the oxalate. So it is S, it is S, it is S squared, calcium and the oxalate, S and it's S and it's S squared. So when you look up the KSP values, for the magnesium, it is 8.5 times 10 to the minus 5. And for the calcium oxalate, we already had that one at 2.3 times 10 to the minus 9. So when you get your solubilities, this is 9 point something times 10 to the minus 3. And this is 4 point something times 10 to the minus 5. That's actually 4.8 times 10 to the minus 5, and that is 9.2. Okay. All right, and so we see that our solubilities, all right, so obviously this one is more soluble, this one is less soluble. All right, so your magnesium oxalate is more soluble. All right, and so the question is, which of the two compounds is more likely to dissolve? So that means that your molar solubility would be a higher number. All right, and so the magnesium oxalate is more likely to dissolve because it has a larger solubility. But adding the acid, both of them will increase by the same amount because they're making the same acid. All right, metal sulfides. If you look at your KSP chart, you will find a bunch of metal sulfides. And sulfides you form by adding hydrogen sulfide gas. So H2S gas is called rotten egg gas. It smells terrible. I did this reaction one time and said, yep, never again. It smells terrible. All right, so you have your metal sulfides. They are insoluble, but they will dissolve in acidic solution because they form H2S aqueous, which is a weak acid. And so if you want to make them be more soluble, you would add acid and make them more soluble. All right, and so you will have a lot of metal sulfides, and you're going to have pH questions using your metal sulfides in order to separate a mixture of your metals. So a lot of times, like the copper and the iron, I should have thought of sulfides. So you would have your FeS versus your CuS. All right, and so then one of those is going to have a much lower solubility, which means it's not very soluble, which means it's going to precipitate first. And then you would have the other one still in solution. And you can change the concentrations by just changing the pH of your solution. So metal sulfides, except of course that stinks really bad, but when you're doing things on paper, it all smells the same. All right, let's do this problem. Okay. Let's go. Trying to come up with a good question. Let's try these two. All right, so my question is between a calcium carbonate and a calcium fluoride, which one of these two is more soluble? So the question would be, which is more soluble? All right, and so the quick answer, which may or may not be right, I'm hoping it's not right. So the quick answer is, you see that the KSP here is a much smaller number by a factor of 100. And so you would say, well, since this has a lower KSP, then it is less soluble. And I'm trying to pick this question out so that that's the wrong answer. Pretty sure that is the wrong answer. All right, in order to find which one is more soluble, you can't just look at the KSP. You have to find the solubility. All right, and so when you have your calcium carbonate, it is 1 calcium, 1 carbonate, and so your S squared is equal to your KSP. When you do your calcium fluoride, 1 calcium, 2 fluorines. All right, and so you have your S, and then you have your 2S squared. So this is 4S to the third. All right, and so when you take the 3.8 times 10 to the minus 9, take the square root, you get your solubility, and that is 6.1 times 10 to the minus 5. I'm not sure about the 0.1. All right, and when you take and divide this by 4 and take the cubed root of that, we already did this one, that is 1.6 times 10 to the minus 4. I'm not sure about that. I'm going to push that in. 0.4 times 10 to the minus 11. Divide that by 4 and take the third root of that. And that is 2.0 times 10 to the minus 4. All right, so even though when you looked at the KSP, this KSP was greater than this KSP, that is not going to give you the answer, at least not every time. Of course, that will work sometimes, but I picked this one out so that it didn't work. And so you see that even though this has a smaller KSP, when you solve for S, 2.0 times 10 to the minus 4 is a larger number than 6.1 times 10 to the minus 5. And so your answer is the calcium fluoride is more soluble. So your CaF2 is more soluble than your CaCO3. All right, you can't just look at the KSP. You have to solve for the solubility, the molar solubility S. The one that has a larger number for S is the one that is more soluble. All right, we will do KFs next time, formation of complex ions. The homework is on Moodle for the book problems.